to answer any questions or ask any questions from the Zoom side if you want. We've got several people in the room as well, so we'll just do a dual modality hybrid session here with you guys. I cannot believe it, but somebody mentioned to me just today, I didn't even think of this, that in my syllabus, somehow my grading scale got deleted. I mean, I never even think about it because I always use the same grading scale for all of my classes. And I looked back at my syllabus and, oh my gosh, it wasn't there. Somehow I must have accidentally deleted it when I was changing the dates and tweaking things around a little bit. So let me just tell you what that is in case you were wondering, because I don't use the standard grading scale that is normally used by most faculty. So for this class, what you need for an A is actually just 87.5 or higher. And then for a B, you just need 75 or above. And a C is 62.5 or above. In other words, there's about a 12.5 point scale. Now, I do use pluses and minuses. So within this A range, for example, from 87.5 up to 90, that's going to actually be an A minus. And then from 90 to 97.5 is an A. And then 97.5 and above is an A plus. So within each 12-point range, there's 2.5 at the top and 2.5 at the bottom for pluses and minuses. So it would work the same for the B range. You'd have 85 up to 87.5 would be a B plus. And then 77.5 up to 85 would be a B. And then 75 to 77.5 would be a B minus. And I'm happy to report that a lot of people in this class are currently in those categories that I've already spelled out here. On the C range, I usually don't give minuses. C minus is something I usually stay away from. So for a C plus, you would need to be above 72.5, but then I pretty much make this into a extended interval, 62.5 to 72.5 for a C. So to pass the class, you really need to be aiming for 62.5. There are 3 or 4 people who are unfortunately a little bit below that right now, but we still have a ways to go. We have another midterm coming up and a final. Also, I will re-weight your grade at the end of the semester. So you'll have a homework grade, you'll have 2 midterm grades, and then you'll have a final exam grade. Those 4 components, whichever one of those 4 is your best score, I will upweight what that counts for in your calculation by an extra 5%. And I'll take 5% away, the weighting of 5% away from whichever of those 4 things is your lowest score. So that actually means that the number you see in Canvas for your overall grade is actually a little bit below what you're actually going to have as of that point in time. I can't do the reweighting until I have all 4 numbers in my hands, which won't happen until after the final. But just so you know, there is a little bit of a bump that everybody gets at the end because of my reweighting that I'll be doing. And then I also take into account participation and improvement and attendance and all that kind of stuff. So that allows me to deal with some of these hairline, borderline cases, so to speak, if they happen to come up at the end of the semester. So I'm happy to report that a lot of people are doing really well. I've got the first exam really went well for a lot of people. So I've got some really nice scores. Let's try to keep bringing those numbers up. That's probably why a lot of you are here today to do the review session, so you can hopefully get a good solid foundation for the second midterm, which of course we hope is going to go well also. Okay, so anyway, I apologize for that. Nobody had said anything to me and nobody had asked me about it. Probably everybody was assuming I just used the same old scale that everybody seems to use, but no, I have a little bit of a more stretched out grading curve here. So I will go ahead and erase it now. Now I feel a little bit better that I've at least let everybody know how that's going to go. As far as how the week is looking, don't forget to turn in the homework from chapter 9.3. It's due tonight. I plan to grade those tonight, and that way you should have those feedbacks by tomorrow. And then we just have this week to get ready for the test. There's no other homework to worry about, no other assignments. I just want you guys to study for our our exam that's on Thursday. We will be doing new material in class on Tuesday this week. It won't be covered on the midterm. It's starting a new chapter. You should come to class though, because it won't be that long till you will be tested on it. It's just 3 weeks really till our final after this. So it's gonna come fast and furious from here. So, okay. Yeah, so just as a quick overview for this midterm, just as far as the coverage of it goes, I know this stuff is already printed out in the handouts, but I just like to kind of say a few words about it. Chapter 7 is where this example will start from, and so that's going to be 7.2 through 7.4. This has a lot to do with the Euler function, the Euler phi function. It was one of the first number theoretic functions that we talked about. So properties of the Euler phi function, things like Euler's theorem, how you apply that theorem, and so on, would be important from chapter 7. Chapter 8 is where we talked about the idea of the order of an element. It's the smallest power of that element that is congruent to 1 in mod n. So you can talk about the order of A in mod n. Remember, I even invented my own notation for it, which was not really notation from the book. But orders of elements is super important. Any element that has the largest possible order imaginable, which would be n minus 1, that's the largest order by Euler's theorem, that's the largest order you could have. Any element of that order is called a primitive root of n. And only certain numbers have primitive roots. You'll want to review which numbers those are, make sure you know what those are. And once you have a primitive root in your hands, you can start talking about indices. And so you can take the index of an element with respect to a particular primitive root. So we're going to be reviewing all of this in some of these examples today, but there's quite a bit of material in chapter 8. I think we spent quite a bit of time there. We did at least 2 homework assignments on it, maybe even a little bit more than that. Then the most recent material was in chapter 9, 9.1 through 9.3. So this was all about quadratic residues and solving quadratic equations. I should call them quadratic congruences. And in particular, a lot of times it was just a question of yes or no. Does the quadratic congruence have a solution? And we used this Legendre symbol to denote the answer to that question as either +1 or -1, and developed a lot of properties of that Legendre symbol. The most celebrated and famous of which is that quadratic reciprocity law that we went over quite heavily this past week. I'm not going to ask you to prove that quadratic reciprocity law. I know it took the entire class period to go through that proof on Tuesday, including the lemmas, but you certainly should know the statement of it as well as the corollaries, because you tend to use those corollaries in practice when you're actually calculating the Legendre symbol. So you'll want to know those results even if you're not asked to prove them. And it's not that the proofs are not worthwhile. There's actually a lot of good content in those proofs. So, you might even feel like you want to study those proofs a little bit, not for the purposes of reproducing them for me on the test, but just because there's some nuggets of wisdom in those proofs. There's some math in there that's very pertinent to what we've covered in this section. So anyway, I think that would be worthwhile. And then the last thing I'll say is there was a little bit of a talk on cryptography. And this is in section 10.1. I will admit that I have downplayed the cryptography this time through the class. Basically, I got rid of the term paper. I used to give a term paper on cryptography. I decided with the evolution of AI and so on that it just wasn't as meaningful anymore. So I took that out, but I would expect that you will get a question on cryptography on this exam. That could be RSA, that could be the Hill cipher, the Bijaniri cipher, or just some kind of linear congruence relationship between plain text and ciphertext, because it ties in with some of the other number theory that is involved with modular arithmetic. So I think it would be relevant. If I was to take a stab at it, and I have not written this test yet, But I would, if I were you, I would be kind of expecting approximately 30% on each of the first 3 chapters, with maybe one question or maybe a couple of parts of questions, adding up to only roughly 10% on that cryptography section. It is, after all, only one section, and we only did one quick assignment with just a few problems on it. But you should be ready for that. In terms of what I'm going to provide you with, on this exam, I'm going to let people use a calculator. However, please do not just expect to show up with your cell phone to use that, because a lot of people will have a phone with a calculator on it, but I'm still going to say no phones. So you need to come up with a different calculator. Please don't come in here with like a huge laptop either. This should be like just one of those basic $5 calculators off of a shelf at Walmart. I'm not looking for a calculator that can do a whole bunch of functions for you. It should be used for addition, subtraction, multiplication, and division primarily. Okay, so just be careful. If you're not sure if I'm going to accept your calculator, you may want to show it to me ahead of time. The math department will also check out calculators for us. So my plan is to check out 2 or 3 for myself and bring them here just in case somebody walks in and has a calculator that I'm not happy with. I'm generally not a calculator type of guy because everybody comes in with a different calculator, and I just don't like trying to make sure that the playing field is even for everybody. But in this case, I think it would be reasonable to use a calculator. Keep in mind that any button pushing you do on that calculator is not going to actually be on your paper. You would need to write anything down on your paper that you want me to grade. And if it's not on that paper, then as far as I'm concerned, it doesn't exist. Like, I can't grade you on something that, you know, you punched into a calculator, but I never got to see you do it. I'm only saying this because I've seen people punch stuff into calculators wrong. I've seen people not understand order of operations with their calculator, and they get numbers that don't make sense. So make sure that I'm not going to make the test heavy calculator. Let me just tell you that right now. It's not what I'm here to test you on. But as a tool to help speed up some of the mundane computational stuff, it might be good for you to have it. But it's not going to be a make or break kind of thing. Having said that, make sure you're writing onto your paper the stuff that's important, because that's what's really going to get looked at, obviously. Okay. The only other things that I might give you on the exam, if I do have a cryptography question or two where I want you to convert from an alphabet to a numerical equivalent system, I would provide you with maybe a table. So the letters of the alphabet correspond to the numbers from 1 through 26 or 0 through 25 or whatever. I would try to provide that framework for you. So you might have a table of values for that. The other thing that I am likely to do is to reproduce for you this table. I might just print one out for everybody. This table of prime numbers up through 10,000. I think it goes up through 10,000. Just so you know, you're not sitting there wondering whether a certain number is a prime or not. I might do that. This table also has, there's also the least primitive root for each of those primes is listed here. So remember that when you're talking about primitive roots, every prime has a primitive root. And so, well, what if you needed to have one in front of you to be able to use? This table would be able to provide that to you. So you can expect that I'm going to give you this table, or at least a subset of the table to use. Because I'm not going to make the numbers always just super, super, super small. So if I'm letting you use a calculator and if I'm giving you this table, I can have a little more flexibility. I can feel less guilty about 2-digit, 3-digit, and 4-digit numbers showing up on the test, because I know that you'll be able to look those things up pretty easily. Okay, so I will be providing a few of those things for you. The conversions for cryptography, as well as, which, by the way, as you know, the RSA crypto system is the one where you have to do high power calculations with numbers. That's a great place where the calculator would be handy, right? So that would be a kind of place where I might write a question where I'm expecting people to use their calculator. Your first thought most of the time on this exam, guys, should not be, ooh, how do I use my calculator for this? It's probably not the main point, right? It's normally not going to be what I'm really trying to test you on. Okay, but I will let you use a basic calculator. I will let you use a conversion table for any of the crypto system problems I might ask. And then this list of prime numbers with small primitive roots, with the smallest primitive root, I think that could be helpful as well. So I'll give you all of those things. Okay? Any questions so far? Okay, if not, as you know, there's a review packet, there's a sample midterm, all that stuff. I don't want to do any of that now because you can do that on your own for your own personal practice, and you can look up the solutions later. What I would like to do is a handful, about 7 or 8 problems here with some follow-ups and some side comments and so on to go along with them that I'd like to have us go through. And I think it's relatively comprehensive, maybe not perfectly so. I didn't think that hard about this. So what I mean by that is don't just assume that if I didn't talk about something from the topics today that it won't be on the test. This is just kind of taking a stab at it. I'm sure that this stuff is very helpful and very relevant, but you should not take it as a sign that, oh, well, he's not going to ask us about such and such topic because he didn't say anything about it in the review session. You still need to review everything on this review sheet, whether I go over it right now or not. Okay, so just to be totally clear about that. Okay, so but does that sound good? Does anybody have any questions before I jump in with a few problems here? Okay, well, let's just jump right in. I'm gonna just make problems that will hopefully touch on the topics that we've just kind of reviewed briefly now. And I'm gonna go in kind of a random order. So the first one is going to be to compute the Legendre symbol of 14 with respect to 137. And I want to say something about this before we even go into this problem. You can assume if you see this question that the number on the bottom is a prime. So if you have a doubt, oh, I wonder if that's prime or not, you know it has to be. The notation does not make sense if the number in the bottom of this Legendre notation is not a prime. So 137 has to be a prime. And this would just be asking you to figure out whether this is equal to 1 or -1. You will get no credit for having the answer correct. Your credit will come completely from all of the work that is shown along the way. And you should try your best to not just have ones and -1s flying all over the place that sort of show up out of the blue. Try to cite things that you can cite, break it down step by step so I can see when you're using the properties and that you know the properties of the Legendre symbol. So that's really how I'm going to be grading something like this, is on a very careful step-by-step methodical process here. So I would love to take some suggestions from you guys on how to maybe start working on this. Let's try to write up a good solution here.
Split it into 2 and 7.
Okay, so one of the properties of the Legendre symbol is that the 14, that whatever number is on top, can be completely factorized. So let's do that. So I'll write the Legendre symbol of 14 with respect to 137 as the Legendre symbol of 2 with respect to 137 times the Legendre symbol of 7 with respect to 137. Now, if you wrote that step explicitly down, I would be great with that. Where I would run into trouble is if you didn't write that down and you just jump to the next step directly, putting 1s and -1s in. Okay, so try to do it step by step. I don't expect you to remember like which exact theorem this was. You don't need to remember theorem numbers from the book, because I happen to know off the top of my head, and I want you to review these properties a little bit. I will tell you this is theorem 9.2 in the book so that you can look it up, but you don't need to tell me that. If you wanted, you could just say property of Legendre symbol. That's a perfectly good justification. In this case, it sort of speaks for itself. So I can tell exactly what you're doing when you go from the left side to the right side here. So if you didn't even say anything right here on this step, that would be okay, as long as this step was explicitly written down and not just skipped over. Okay. Any thoughts on what to do from there?
Symbol for 2 for 137 is.
Mhm.
I'm figuring out.
Okay, so we have two things to calculate here, and they can kind of be done independently. So what is being suggested here, I think, is to just focus on each of them one at a time. And let's focus on the Legendre symbol of 2 with respect to 137. Do we have anything that would help us with that?
Yes, we have the property in which if P is congruent to 1 or 7 mod 8, then that would be a 1. If it's -1, it would be P is congruent to 3 or 5 mod 8.
Thank you, Kim. That's exactly right. I appreciate that. This was actually theorem 9.6, which we just talked about a couple of days ago. This tells us the Legendre symbol of 2 with respect to NA prime. The main thing is we have to calculate in mod 8 what 137 is. So to do that, you'd have to take 137, divide it by 8, and focus on the remainder, right? So if I do that, if I divide, if I divide 137 by 8, I'll get a 1 here, and then 57. This becomes 7, 56. It looks like the remainder is 1. Okay, so the remainder is 1, and if it's a 1, then this number is a 1. Okay, and if you didn't remember the theorem number, that would be okay, but I would want to know why you're saying this, because if you just write this down, I'm going to think, oh, they just guessed the answer. So your thought process when you're showing your work on the midterm should be, let me make sure that he can't say that I was just guessing the answer. So what you would want to do if you didn't remember the theorem number, if you remember the theorem number, great. But if you don't remember the theorem number, you could just give what would be the reason, which is you could say since 137 is congruent to 1 mod P. That's the substance of what theorem 9.6 says. So you can either cite the theorem, or you can cite something about what the theorem says that justifies this step. If you just write it down with no justification, then you're going to fall into the category of, oh, it was a 50-50 shot and they guessed the answer, right? That's not what I want to see. So please be sure to justify that answer. Okay, so this one is a 1. Then we obviously have to calculate the other one. So next, let's look at the Legendre symbol of 7 with respect to 137. Does anybody have any suggestions about how to calculate that one?
We want to flip it, and then we want to look at the rules in P is congruent to 1 mod 4, and P is congruent to...
Thank you, Kim. Yes, exactly. I want to use the quadratic reciprocity law. These are 2 distinct odd primes. So you always prefer to have the smaller number on the bottom, because you can then reduce modulo that smaller number. So that's why it's being suggested here that we flip this over. The question is, do I have to do a sign change when I flip this over? That would only require a minus sign if both of these numbers are congruent to 3 mod 4. Okay, now 7 is congruent to 3 in mod 4, but 137, if you just look at the last 2 digits, divisibility by 4 is based on the last 2 digits. Well, 36 is a multiple of 4. So in mod 4, 137 is just 1. So it is congruent to 1 mod 4. So this one flips over with no sign change at all. Again, you can state the theorem, which was 9.9, or if you prefer, you can just state, you could just say by the QR law. If you say that, I'll know what you mean. Quadratic reciprocity law, that would be fine. And once you've done that, then you can reduce what's on top in mod 7. So now I have to take 137 and divide it by 7. So again, I need a little bit of scratch paper here. If I take 137 and divide it by 7, it goes in there, I guess, 19 times with a remainder of 4. Yeah. So it has a remainder of 4. The remainder is what you care about. So I'm going to end up with the Legendre symbol of 4 with respect to 7. And is that equal to +1 or -1?
They were
It is
equal
plus,
one.
it is +1, thank you very much, because 4 is a perfect square. Okay, again, this could be, if you wanted to cite this one, theorem 9.2. Okay, so the final answer is a +1, and again, the final answer alone without any of the work would be worth very little to me. It would look like it was just a guess. But anyway, we now know that 14 has a square root in modulo 137. Is everybody comfortable so far? Let's ask a follow-up. How could we find the square root of 14 in mod 137? So let me put that over here. The Legendre symbol doesn't help me actually find the solution to the quadratic congruence. It just tells me yes or no, will there be a solution? So to decide what the solution actually is, we would have to go a bit further. So how could we solve for x? So here's my congruence, x squared congruent to 14 modulo 137. And let me move my camera over a little bit closer here. Yeah, so this would now be the question that we might want to ask. Does anybody have any thoughts about this? Notice I've picked a modulus that's pretty big. You know, you're probably not going to want to like square every number from 1 to 136 to figure this out. Okay. Do we have any thoughts about how we might be able to approach this one?
If you were to subtract 137 from 14 in a way where that number ends up being almost like a perfect square, then, or add them.
So you can add and subtract multiples of 137 all day long. That's kind of stabbing in the dark. It's sort of saying, oh, let's just hope that if we rewrite this number in a different way, that it will be obviously a perfect square. But it's a bit of a stab in the dark, I would say, because it's not clear that you're going to ever get a number that is, I mean, we do know that there's a square root here, but we don't know how easy it would be to see it.
Or you could use the formula b squared minus 4ac.
Okay, so that is something else. Let me come over here for a second. So if I start off with a congruence like this, so this is good just to review really quick, but this is not what we're going to need for this problem. But if we have a quadratic congruence like this, what we could do is we could change the variables of it. If you remember, we can replace basically we can make a new variable d, which is just b squared minus 4ac, and then we can make a new variable y, which is coming from 2ax plus b. And using that change of variables, we can create a new congruence. Just make sure I have this exactly the way I want to. Yeah, so we can take a quadratic congruence of this form and then rephrase it like this. But the problem is that the new congruence would then be y squared congruent to d modulo p. But we are already looking at a congruence that has been simplified into this form. We're not starting with a generic quadratic form and trying to change variables on it. What would be a good problem here would have been if I had given you something like this in such a way that b squared minus 4ac was equal to 14. Then it would have led us exactly to that problem there. So in other words, if there could have been a part A ahead of this that would have been written as a quadratic congruence, which we could then change the variables on and end up asking this question, right? But we're already in the most simple form here. We're already in the most simple form here. So we can't really do anything to make it any easier than the equation that's already written here. Any other thoughts about how we could tackle this?
Can you use indices?
Can you use indices? Well, let's imagine that we are working in a modulus, which is prime, and all primes have primitive roots. If I'm going to use index, I would have to use primitive roots. So if I think about it from that point of view, we could say, let R be a primitive root of 137. Now, if you're wondering, well, how are you going to get a primitive root of 137? That would be something in the table that I'll be giving you. So if you look in the table in the book, there is a place where it would give you the least primitive root. And so 137 is here, and it tells you in the book that R equals 3 is a primitive root of 137. So you could just work with that value. By the way, once you have one primitive root of a number, you can generate all of the other ones as powers of this one. Which powers? They are the not all powers. It's not every power. It's just those powers of R that are relatively prime to phi of n. In this case, phi of 137 is 136, and so you would have to take phi of that. So remember that the number of primitive roots, this is just a quick reminder, the number of primitive roots of n, if there are any at all. Okay, could be 0, right, guys? Could be 0, but if there are any primitive roots of n, the number of primitive roots is phi of n. That's a good thing to just memorize that one. And so if you're talking about 137, then you would need to calculate phi of 137, and that would be phi of 136. And to calculate, now I'm kind of going off topic a little bit here, but to calculate phi of 136, you have to use properties of the Euler phi function, namely that it respects multiplication if you break this into prime factors. So 136, you'd need to divide it into prime factors, which I think it goes in there 8 times with a remainder of 7. Just a second. No, 17. 17. There we go. Yeah, 136 is just 8 times 17. And then phi of 8 is 4, and phi of 17 is 6. So you would end up getting 64 primitive roots for the number 137. And how you could take the first primitive root, which is R equals 3, and find the others would be that you would raise the R to the 64 different powers of R that are relatively prime to 136. Yeah, so you'd have to go through. So you'd skip over R squared. That wouldn't be a primitive root. So you'd go on to R cubed. I mean, so for example, I would know, so any primitive root of 137 should have order 136. It's always one less than whatever the n is that you're working with, right? Well, but the thing is, so if it's really true that the order of 3 in mod 137 is 136, then I can already tell you that the order of 3 squared will only be 68. It will be half of 136 because I can take R squared And what power of that do I need to get back to 1? Well, if I take r squared and raise it to the 68, that's as if you just took r and raised it to the 136. So your order of r squared is too low. So you'd skip over that one. The next primitive root would actually have to be r cubed. This 3 is relatively prime to 136. So you could just keep playing the game like that. Anyway, I'm getting sidetracked. This whole topic about primitive roots and order and so on. I want to come back to what Stephanie suggested, which is that we use primitive roots to solve this congruence. And it's a great idea. It's a great idea because what you can do anytime you have a congruence that's valid, if you find yourself a primitive root, you can reduce the congruence modulo that primitive root, sort of using the index idea. It's like taking a logarithm of both sides of the equation, right? So in other words, the index relative to r of x squared would be congruent to the index relative to r of 14. And the only thing that you have to be a little careful here is that the modulus on an index equation is always modulo phi of n. So if this was mod 137, the modulus for the index equation should be phi of 137, which is 136. So this would be a 136. Okay, so far so good. And your ultimate goal here is to solve for x. So you want to somehow isolate the x. One possible thing that would help you to do that would be to use the properties of index. And remember that they're all the same properties that you know for logarithms. So like, for example, if you have the log of x to a power, you can pull that power down in front. So we can do that here. We can pull this 2 down in front to start to try to isolate the x a little bit. Now, I would do this one step at a time. So this is, again, I probably wouldn't expect most people to just have the theorem number from the book off the top of their head right now, but this is just property of index. And if you just write that down for me, don't let that throw off your momentum. Just give me a quick little, just jot it down so I know that you have an idea what your game plan is. Are we okay so far?
And here r would be 3.
So we would, actually, this would be true for any value of r, but if we're using the table and we don't have any other values of r around, then you could choose to take r equal to 3. So I could go ahead and just plug that in now. Mod 136. So this is just choosing r equal to 3 in order to make that work. Now, the thing that's going to be the problem here is you have to calculate the index of 14 relative to 3. In other words, you have to figure out what power of 3 to what power would give you 14 in mod 136. This is basically the question that you would have to answer. And that is something that is likely not to be obvious.
Is that mod 137?
Oh, yes, sorry. This one is mod, because we're not on the level of indices anymore. We're back on the upstairs level. So yes, that should have been in mod 137. So I have to calculate some exponent of 3 that's congruent to 14 in mod 137. That's going to be not easy just off the top of your head. So what would have to happen there is I might give you a table of indices. So instead of giving you this whole big table here, well, maybe in addition to giving you this whole table in the book, I might also, for this particular problem, give you a table of indices for a particular value of r and a particular modulus n. And then you can read it off of that table, right? And then from that table, you figure out what this number is. Once you know what this number is, you just have a linear congruence here. Okay, and I should mention, I'm not going to ask you any questions on this midterm that I could have asked you on the last one. So linear congruence is sort of belongs in the material from the first part of the course. I won't ask you a standalone question about stuff from earlier, but that doesn't mean you don't need to know any of that stuff from earlier. I would still want you to be able to solve this thing for the index of x relative to 3. Okay, so I actually don't know what this number is. So we won't be able to really do the problem fully right now, but you would solve for this value, and as soon as you know what the index of x is, so if I know that the index of x relative to 3, if I know that it's equal to, I don't know, let's just make up a number, 5, then I can solve for x. X is just 3 to the 5th. Again, it's just exponentiating both sides, sort of undoing this logarithm operation to solve for x. So if you have your table, you have a top row and a bottom row of that table. We're going to do an example with a table of indices and all that stuff in a little bit. But you'd be able to use a table to then solve for x once you knew what the index of x was. Okay, so I guess if I didn't want to give you a table, but I wanted to make a nice problem out of this, instead of asking you to actually solve the congruence, what I could do instead is a slightly different question. Maybe I'll just change my question here a little bit. This would be a different follow-up that we actually could completely do, which would be to prove for any primitive root r of 137, the index relative to r of 14 is even. Now, I just want to imagine for a second that I hadn't asked you this first follow-up at all. I didn't ask you any of this. We didn't do any of this, right? Having this as a follow-up to that question right there is a little bit bizarre. It's like, okay, well, they calculated the Legendre symbol here. We got a +1. What does that have to do with proving that this index must be even? Well, the idea would be that, okay, x squared congruent to 14 mod 137 has a solution for x. This was a +1, right? It has a solution. If I take this congruence and I apply index to it relative to any primitive root r, I'll get basically this right here. And from here, you can see, because remember the condition for this linear congruence to have a solution? The GCD of this number with this number has to divide this number. You remember that? So if I have, if I just have a basic linear congruence, AX congruent to B mod N, this goes back to earlier in the semester, but this has a solution if and only if the GCD of A with N divides B. So actually this top line here is in that format, right? Here's A, here's the unknown, here's B, and here's mod N right here. So you could answer this follow-up question after having checked that Legendre symbol. So it would be a way of asking a nice question about using indices in this problem without having to have a table in front of you. Does everybody see that? I don't have to give you a table anymore. All you have to do is start from here and say this has a solution. If this has a solution, then this is just an algebraic manipulation to get from here to here. And this congruence here, this is like A times X congruent to B mod N, right? You can literally think of it in those terms. And you're just trying to prove that B is even. And it has to be because B is a multiple of the GCD of A and N. Assuming you know you have a solution, which is what that part of the problem explains, right? Then you would know that this is the case. So it's kind of interesting. The stuff on quadratic residues could be used to make a statement about the index of a number relative to some primitive root. I think that's kind of a nice, it's maybe an unexpected connection between those topics, but I kind of like it. Yeah. Okay. So far so good. Okay, let's go on to another problem. Bring my camera back over here. This side. Let's do this one, which is, this will look somewhat familiar. It's kind of related to the group work that we did on Tuesday and one of your homework problems for tonight. Let's prove that if P greater than 3 is prime, then the Legendre symbol of -3 with respect to P is equal to, of course, it's either equal to 1 or -1. Let's try to prove that it equals 1 if P is congruent to 1 in mod 6, and -1 if P is congruent to 5 in mod 6. Yeah. Now, these are actually the only two possibilities for a prime to be congruent to in mod 6. Assuming it's bigger than 3, right? If P was congruent to 2 or 3 or 4, then P actually wouldn't be able to be prime. Because if P was congruent to 2 or 4 in mod 6, it would be even. And if P was congruent to 3 in mod 6, then it would actually be divisible by 3. And so that wouldn't be a prime either. So if P is bigger than 3, the only kind of primes you can have are the ones that are congruent to 1 or 5 mod 6. I'm only making this point because every scenario has to either give you a 1 or a -1. There shouldn't be any other cases where, oh, it's not covered by the formula. The formula should handle every single possibility for P. And in the world of mod 6, technically there's 6 possibilities. But what I'm trying to do is rule out 4 of those 6. That in mod 6, your P cannot be 0, 2, 3, or 4, or it wouldn't have even been a prime in the first place. Is everybody following that? That seem reasonable? Okay, so any thoughts about how to tackle this one?
The cases,
We're probably gonna want some cases, yeah. And what kind of cases are you thinking about?
the form P has to. What is it? P is gonna be like 6K plus.
Okay, so the P, we could do the cases based on this if we wanted to. I actually think it'll be easier if we don't base our cases on the options here, but rather if we line them up better with theorems that we already know.
We can use the Lagrange symbol and split up the -3 with respect to P to be -1 with respect to P times 3 with respect to P.
Okay, so what Kim is suggesting is, which might help us with the cases a little bit, is that we use the property of the Legendre symbol that I can split it apart under multiplication. And the thing is that we already know the Legendre symbol of -1 with respect to P. So let me just recall that the Legendre symbol, this is one that you guys would want to know. The Legendre symbol of -1 with respect to P, it's 1 if P is congruent to 1 in mod 4, and it's -1 if P is congruent to 3 in mod 4. Right, so this is, I forget if this is this, I think this is theorem 9.1. Hope I'm giving the right numbers here for my theorems. No, that is not theorem 9.1.
This
I'm
should be
sorry.
theorem 9.2e.
Yeah, I'm sorry. You're right. That is part of theorem 9.2, part E. Yeah, thank you. I cited the wrong result there. Okay, so we would know this one already. And then it becomes a matter of looking at the Legendre symbol of 3 with respect to P. We don't have any standalone theorem for that right now, but what you will want to do with this is flip it over. Notice that P is larger than 3, so you would like to flip this over, but in flipping it over, you might have to do a sign change. The one that was in the group work this week, I think we were looking at the Legendre symbol of 5 with respect to P, and so you were always able to flip that one over with no sign change because the quadratic reciprocity law says that as long as one of the two numbers is congruent to 1 mod 4, such as 5, then you can flip it over with no sign change. This one cannot just be freely flipped over. So let's just maybe do it like this, guys. I'm going to either get the Legendre symbol of P with respect to 3 or negative of P with respect to 3. And over here on the far side, I'm just going to say the first one is if P is congruent to 1 in mod 4. And the second option would be if P is also congruent to 3 in mod 4. Okay, so it just is going to depend a little bit on that. Okay. Now, what about the Legendre symbol of P with respect to 3? Of course, I'm going to reduce the P down to either a 1 or a 2. And actually, what we know about that is that this one would be a +1 or a -1. I'm going to do little cases within cases here. It would be a +1 if P is congruent to 1 in mod 3. Like, what are the quadratic residues of 3? You're just simply looking at 1 squared and 2 squared. And in mod 3, the only perfect square that you get is 1. 1 is equal to 1 squared and also -1 squared, which is the same as 2 squared. But 2 is not a perfect square. Remember, this is a good review. Exactly half of the numbers are perfect squares and half of them are not. And when I say perfect squares, that's just my fancy lingo for quadratic residue. So here, 1 is a quadratic residue, 2 is not. So my other case is going to be if P is congruent to 2 in mod 3 is going to be a no. Yeah. Okay. And the second line, guys, the second line is going to be essentially the same thing, but with the opposite signs. So we'll have -1 if P is congruent to 1 mod 3, and we'll have +1 if P is congruent to 2 in mod 3. Okay, hopefully that's making sense the way I've written that there. What I'm going to do now is I'm going to go back to Weston's original idea of doing cases, and I now sort of know how I want my cases to be laid out. There's the issue of what is P congruent to in mod 4, and then there's also now the issue of what is P congruent to in mod 3. And I've always got, for both cases, I've got 2 choices. There's 2 options here, and then there's 2 options here. So this is going to make 4 cases. And let's try to write them down. Okay, so let's take Weston's idea now and get our cases going. But again, I would rather do my cases based on this calculation than just from what's up in the original question. So case 1 would be P is congruent to 1 mod 4 and P is congruent to 1 in mod 3. And what you'll want to do here, guys, is you'll want to come back to your work over here and say, well, where am I going to end up on my little spreadsheet here, right? If P is congruent to 1 in mod 4, then I'm in this part of my diagram, right? And if P is congruent to 1 in mod 3, then I'm supposed to get a +1. So in this case, what we would say is that the Legendre symbol of 3 with respect to P is +1. And we already know that the Legendre symbol of -1 with respect to P is 1, because that's actually covered by this case as well. So putting that together, my Legendre symbol for -3 with respect to P would be 1 in this case. Okay? And by the way, that is the case where P is congruent to 1 modulo both 4 and 3, which actually means that P is congruent to 1 in mod 12. And that would be the first case. Okay. So let's keep going. I'm gonna go all the way through this one to make sure we totally have the whole thing down. Let's look at case 2. Is everybody ready for case 2? Do you understand how I'm doing this? This is a good time to ask if you're not sure what I'm doing. And there's a likely chance I'll ask you something like this. Between the group work and now this problem, and there's also one on the homework, I like these problems. I do like these kind of problems. So be ready for it. It's always going to come down to looking at cases like this. Now, another possible case would be P is congruent to 1 in mod 4, but P is congruent to 2 in mod 3. Yeah, this is a good case. And in this case, let's figure out what our Legendre symbols are. The Legendre symbol of 3 with respect to P. So now I'm looking at the stuff on the bottom here. P is congruent to 1 in mod 4. That's the part in the box. But since P is congruent to 2 modulo 3, we're supposed to get a -1 here. So this one would be a -1. However, at the same time, the Legendre symbol of -1 with respect to P is still +1 from right here. P is congruent to 1 mod 4, gives me a +1 on the Legendre symbol of -1. So putting this together with the multiplication property, this one comes out to -1. And we can ask ourselves, okay, well, what case is that? If P is congruent to 1 in mod 4 and it's congruent to 2 in mod 3, technically this is a Chinese remainder theorem problem, but if you can do it in your head, I'm okay with that. Like, you could solve this congruence just by experimentation. You've only got 12 numbers at most in mod 4 and 3 combined. There would be 12 different scenarios you could have. And so I would be totally comfortable with somebody just running through trial and error to figure out what P is. Can anybody tell me what it's going to be? It looks like 5 to me, right? In mod 12, right, 5 is congruent to 1 in mod 4 and is congruent to 2 in mod 3. So that would be just something you could see by inspection. You wouldn't need to give me a whole long spiel on that. Okay, let's go to the third case. Case 3. This one would be, now we're going to do P congruent to 3 in mod 4, but we're going to still do P congruent to 1 in mod 3. So this would be the third case. And by the way, let's just, while we're at it, before I go any further, let's figure out what this would be in mod 12. I can just trial and error this one away, and you're going to immediately see that P is congruent to 7 is a solution to both of the congruences. So how am I getting these? Just by inspection, by the way. I'm just plugging in a number here for P that's somewhere between 0 and 12, 0 and 11, I guess, and just seeing which one works. Okay, in both. It has to work in both of those congruences. And 7 would work in that case. Now for this one, let's do our Legendre symbol of 3 with respect to P. So if we come back over to our notes on the first part of the solution, if P is congruent to 3 in mod 4, then, sorry, it's congruent to 1 in mod 3. P is congruent to 1 in mod 3, then oh, I'm sorry, and we're in this case here. I forgot about the part on the side here. So P is congruent to 3 in mod 4 means we're looking at the bottom 2 rows here. And then we're in the case of P being congruent to 1 in mod 3, so we get a -1. Yeah, I just lost track. We have to remember this goes with this box, and this one goes with the cases down here. Exactly right. Okay. So because we're flipping them over, and we're trying to remember when do we have to do a sign change. So in this case, we do have to do a sign change on flipping it over. So we want to get -1 for the Legendre symbol of 3 with respect to P. That would be a -1. And for the Legendre symbol of -1 with respect to P, since P is congruent to 3 in mod 4, this would also be a -1. And so my final answer for the Legendre symbol of -3 with respect to P is the product of -1 times -1, which becomes +1. Okay. Last but not least, case 4. This would be P is congruent to 3 in mod 4. And P is congruent to 2 in mod 3. That's the last combination that we need. And if you put those together, you'll see that P would be therefore congruent to 11 in mod 12. And for this one, let's work out our Legendre symbols again that we need here for both 3 and -1. So for the Legendre symbol of 3 with respect to P, again, I'm in the bottom case here. P congruent to 3 mod 4 and congruent to 2 mod 3, which gives me a +1. So that first one is a +1. And the Legendre symbol of -1 with respect to P would end up being a -1. And putting that together, we would get the Legendre symbol of -3 with respect to P as -1. Now, here's the thing. Although we did 4 cases and we needed to do all 4 cases, there was no way to compress this into only 2 cases, by the way. This is a 4-case problem. But what the question did was a little tricky, because what it did is it makes it look like there's only 2 cases. It compressed the problem down to look like there are only 2 cases because they expressed the answers in mod 6 instead of mod 12. But if you'll notice here, guys, if you look at cases 1 and 3, those are the cases where we end up with a +1 for our final conclusion about our Legendre symbol here. Right? In cases 1 and 3, what you're talking about is P congruent to 1 mod 12 or 7 mod 12. Those 2 cases, case 1 and 3, have been compressed into one single case by reducing it to mod 6. If you think about it, in mod 6, both of these cases are the same case, which is that P is congruent to 1 in mod 6. You with me? This problem would have been easier if instead of 2 cases here, I had listed it out as 4 cases in mod 12. And then you would have said, oh, okay, that's perfect. That lines up with the 4 cases of work that we did. But then what the question does, and they weren't even nice enough to give us a hint, the question compresses the 4 cases into 2 cases of 2 each. If I do take cases 2 and 4 together, those are both, so P being congruent to 5 or 11 in mod 12, that is equivalent to having it be congruent to 5 in mod 6. So this is absolutely, it's a little, what I'm trying to say is it's a little bit deceptive. It's a little bit deceptive because And this is where if you tried to start with just what they gave you with these two cases, you would find it more challenging to know how to kind of proceed with the problem. Because I mean, you would say, well, okay, P is congruent to 1 in mod 6, but what I have information about is 3 and 4 here. So that would be a little bit more challenging. What do you guys think? Does this seem okay? So this is the Legendre symbol for -3 with respect to P. We've got the Legendre symbol for 2 with respect to P, which we know. The one in the homework is 6 with respect to P. The one in the group work was 5 with respect to P. So you should be fully expecting me to find some other number that's close to one of those and put it on the test. And if you really want to get ready, what you could do is pick one of them and try it with your friend. Say, let's just figure out the Legendre symbol of 10 with respect to P. And just see if we could say something about it, right? You could kind of make a little bit of a competition about it. Just see if you and your friend can work on it separately, come up with the same answer, and explain it to each other. I actually think a lot of this material, you guys can easily make your own problems, and you can practice them pretty easily. Just calculating Legendre symbols, yeah. Pick any value of A, pick any prime P, and just calculate it. And then give it to 3 other people and see if they all get the same answer. Like, are you all getting the same calculations to work out? Definitely something worth doing.
So like it was 10 over.
Yeah.
Would that be like 6 different cases? Like,
I would break it down as the Legendre symbol of 2 with respect to P and 5 with respect to P, I think.
I was thinking -10, sorry. Yeah.
Oh, yeah, for -10, you'd probably first have to break it as -1 and 10. And then for 10, you'd have to possibly break that down into 2 and 5. I could see that being 8 cases. And maybe they would collapse down into less than 8 cases. I'd have to work that one out. Why don't you try it? give yourself a little assignment to see if you could do it. Yeah, pick your favorite number. Don't make it too big, but something that'll only have a small number of cases. Yeah, you could certainly do that. Okay, let's do another problem, guys. I hope that this is feeling like familiar stuff so far. I'm kind of just going with the material as we see it from this syllabus for this exam. So I'm not trying to do anything too far off of the mainstream here. So let's go to number 3 for the review. And let's let P be a prime such that 2P plus 1 is not prime. So we'll start with a prime number, but after you double it and add 1, that you don't have a prime. And then what I would like to do is prove, there is no integer little n, no natural number little n, with phi of little n equal to 2p. So I'm going to go away from the Legendre symbol for a little while and talk about the Euler phi function. So this is now taking us back into chapter 7 a little bit, kind of some of the earlier material. So one thing to make sure you're ready for on Thursday is that you know a lot about the phi function. You should definitely know the definition. This is the number of integers between 1 and n that are relatively prime to n. You should know that. You should know the formulas for phi of n. Well, when I say formulas, there's like several different rearrangements depending on how you factor it. The one that I like the most, the one that's sort of the most general applicable formula for phi of n comes from theorem 7.3, which is just that it's n times the quantity of 1 minus 1 over p1, and then 1 minus 1 over p2, and so on, where the p's are just the distinct primes that occur in the factorization of n. You're going to want to know that formula. remember that, phi of, if you take a power of a prime, you're gonna wanna know that that's just p of k, p to the k minus p to the k minus 1, stuff like that, right? It would be good to know. Also, I forgot to mention that on your exam, I will be asking you to prove a few theorems, and there are a couple of them from chapter 7 that involve the Euler phi function. So this is the list of theorems. It's in the review handout, but while I'm thinking about it, I will just mention this. As it turns out, they're all from chapters 7 and 8, the theorems to prove. I'm going to put 4 of these 5 theorems on the test. I will state them for you on the test, and you will have to choose 2 of those 4 to write down a proof of. So you will have some choices about that, which ones you want to do. Theorem 7.2 is the one that says that phi of m times n is equal to phi of m times phi of n as long as m and n are relatively prime. So that's one of the earlier theorems that we did way back in early March, I believe. So that'll be something you would want to review from a while ago. Certainly, it's an important property of the Euler phi function as well. And anyway, so just wanted to remind you that there is a list of theorems. So if you're like, oh gosh, I don't know what I should study next, if you haven't studied these, that's something you can do on your own. I'm not going to go over all of that right here. Okay. And just like the first midterm, this will be worth, enough of the exam score that you're going to want to do well on this, right? I mean, it's not going to be a huge amount. Maybe 20% of the test will be writing up these proofs. But I would go into that exam and write them down first. I would be ready to go. No surprises. It's almost, I'm picking important results whose proofs are reasonable to write down, but that will also get you confident and get you going. You're not going to walk into the test and just sit there like stuck from the very first moment. You're going to be able, hopefully, to work on these and kind of get into the flow of the exam. Okay, that's my hope with it. And it worked really well for the first midterm. Like I told you guys, that first midterm really, not for everybody, but for a large number of people was really good. So hopefully this will do the trick again and get everybody off to a good start. So let's try, having taken that quick little moment of a diversion, let's try to do this problem, which is actually similar to one of the group work problems that was from a few weeks ago. Proving that you can never get 2 times a prime as the output of phi of n, as long as your prime is of this nature right here. Okay. So by the way, this would not apply to p equals 2, because if p is 2, then 2p plus 1 would be 5, which is prime. So p equals 2 is out. Actually, p equals 3 is also out. Because if you plug in 3 for p, you get 7 for 2p plus 1, which is, again, is a prime. So 2 is out, 3 is out. The first prime for which this actually works is, 5 is out. Because 5 is a prime, but 11 is also a prime. So that doesn't work. The first prime that actually works is 7. Because if p is 7, then 2p plus 1 is 15. 15 is not prime. So this actually implies that p is at least 7. It can't be smaller than 7. If p is 2 or 3 or 5, we violate our assumption in the first place. Any thoughts on how to do a problem like this?
The definition, but that's like equation on both sides.
Mm-hmm. Yeah, we could sort of take the formula for phi of n. I'd like to suggest that we do this by way of contradiction. Suppose that there is an n such that phi of n is equal to 2p. So you're sort of going to start with this equation, and then on the left side, use one of those formulas for phi of n that we just talked about. So yeah, so let's try and set it up that way. I'll start my solution here. So by way of contradiction, BWOC, let's assume that phi of n does equal 2p for some natural number n. So there exists a natural number n such that phi of n is equal to 2p. And then I think what Weston's suggesting is that we use the formula for phi of n right away. So then we have, let's see, the formula for phi of n is n times 1 minus 1 over p1 times 1 minus 1 over p2, dot, 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 up to 1 minus 1 over pr. And this would equal 2p. And this is where we should probably write down what n looks like. So n would have the form, for that to be true, n would have the form of p1. I think I used a k1 when we originally wrote this down. And then p2 to the k2 and dot, dot, dot up to pr to the kr. And these exponents, they all need to be at least 1. Those k's have to be at least 1. Otherwise, the prime isn't even really there. And we wouldn't have written it down in the first place. So we'll just assume that that's the nature of our number. Okay. Any thoughts about what to do from here?
Divide both sides by 2.
We could divide both sides by 2. I don't think I'm going to do that, however. The real thing you want to do is turn both sides into whole numbers. I don't like having fractions showing up because I want to say things about divisibility on both sides of the equation. So what I would actually recommend that we do is, and we've done this before, I would try to like make common denominators out of things, and then that way I can like combine things together nicely from an algebra point of view. So I'm going to go ahead and work on the left side of my equation. And the right-hand side is very simple. I'll just leave that alone for the time being. But on the left side, I just want to try to make a common denominator. Now, when I have these primes on the denominators here, every one of those primes just divides directly into n and just pulls the power of that prime down by 1. So I know we've done this before, but this n, when I take this n on the left side and I divide it by all of those primes, I end up just getting all of those primes with one less exponent, right? P1 to the k1 minus 1, P2 to the k2 minus 1, all the way across the way to PR to the kr minus 1. And then we also still have P1 minus 1, P2 minus 1, and dot, dot, dot up to PR minus 1 equals 2p. So the right-hand side is still the same as before. I'm just working on the left side here. And it's just basic algebra that I'm doing, but it's important that we do it carefully and that we recognize the value of doing it. Okay, let me take a look at what we have here. Don't forget our good friend, the fundamental theorem of arithmetic. There's only one way to factor a number. And I can see that on the right-hand side, the one way of factoring this number is 2 times p. There's nothing else to it. This p is not equal to 2. In fact, it's at least 7. So you just have a 2 and a p. And on the other hand, what you're looking at on the other side of the equation looks like a big mess with a lot of factors. It must be that that left side is looking deceptively complicated. It can't really be that complicated. Yeah, so, you could think about this, that the left side has to have a factor of 2 somewhere. and a factor of P somewhere, right? And both of those are primes, by the way. And so let's just talk about the P really quick. There's a P on the right side. That means there has to be a P on the left side. P is prime. So could this be P? No, this is one less than a prime. This is one less than a prime. All of these primes, by the way, these P's are pretty big because N has to be larger than 2P, which means, N is already at least, 14 or more. It's a pretty big number. So this prime factorization here, it is true that one of these primes could be a 2 or a 3 or whatever, but somewhere on the left side, I have to have a P, and P is at least 7. It's not going to be this term. 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 None of these are going to be P because these are not even primes. Unless P1 was 3. If P1 was 3, then when you subtract 1 from it, it becomes 2, which is a prime. But that's not the prime P. P is a bigger prime than 2. So this is not P. This is not P, this is not P, this is not P. So guys, your P that is on the right-hand side and therefore must be on the left side is actually among the original primes in the list from P1 through PR. Let's just assume it's P1 without loss of generality. So without loss of generality, assume that P1 is P. Okay. And how many powers of that prime can we have? Well, on the right side of the equation, I only have 1 power of that prime. So on the left side of that equation, I also have only 1 power of that prime. So what's the exponent K1 going to be? 2, exactly. Exactly. So P1 is P and K1 is 2. So this first term is actually P. So I'm going to cancel it with that P. And then let's write down what's left over after we do that. So I'm going to do a little canceling now. Every one of these arguments is similar, but they're always just a little bit different from each other. So that's why you have to practice them a few times. So let's just cancel that. So with P1 equal to P and K1 equal to 2, we cancel. And when we've canceled, what are we left with? P2 raised to the K2 minus 1 times ... times PR to the KR minus 1 times P1 minus 1, P2 minus 1, P3 minus 1, and ... right? All the way up to PR minus 1 equals 2. That right-hand side is so small. You with me? So I've canceled the P from both sides of my equation, and this is all that's left. This has got to be a contradiction. This has got to be a contradiction. How could this possibly not be a contradiction? Let's just see what we end up deciding here. Is everybody so far so good?
Dr. Annan?
One second, Wes. Yeah, go ahead, Edgar.
Why do we cancel out the P1 minus 1?
Oh, I probably should not have done that. Is that what you were going to ask me? Yeah, you're
Okay.
absolutely right, Edgar.
Okay.
I should not have canceled the P1 minus 1. Let me just squeeze it back in here. I am so sorry. Yeah, the P1 minus 1 is still there. Yeah, the P1 minus 1 is still there. Of course, that is going to be the way we get our contradiction. So I probably was going to catch that in a second, because this P is at least 7. Well, actually, yeah. So So P1 is equal to P, which is at least 7. So P1 minus 1 is at least 6. And so you have a factor on the left side that is at least 6. And there's no way, therefore, that this product on the left could equal 2. Okay. So left-hand side is at least 6. Left-hand side of this box is at least 6. And this is a contradiction, which is a contradiction. All along, that's what we were looking for. We were trying to come up with a contradiction here. So that should pretty well give it to us. Yeah. Okay. Any other questions on that? Any comments on that? Seems okay so far? Okay, let's move on to another problem. So just, by the way, you're not going to walk out of the review like, oh, I guess I'm ready to take the test now. What you're supposed to be doing is making notes to yourself about topics that you're remembering. It's like, oh, I remember we did that back in March. And that was before spring break, so I probably should review it again. There's stuff like that, hopefully coming into your thoughts as we go forward here. Okay, let's move on over here. And I'm going to ask you another question. This is number 4. Okay, so here's the question. Find all primitive roots of n equals 18. By the way, just remember, let's just take a moment. I mentioned something about it earlier, but I just want to make sure everybody knows this. Can you guys remind me which numbers have primitive roots? Because we did this whole, I didn't fully prove the whole thing, but I certainly made a list of this. Does anybody remember what they are?
2, 4, P, and 2P.
2, 4, P, so this would be where P is odd prime P, and then 2P for the same odd prime P. Is that right? I can tell you that if that was right, this question would not make sense because 18 is not in this list. Like 18 is not a prime. It's also not 2 times a prime. So does anybody remember the tweak, Stephanie?
2 times p to the k.
2 times p to the k is correct. So twice a power of a prime. And what else needs to be fixed? The p should also be p to the k. So any odd prime to a power, that could be the first power, so it includes all odd primes, but it could be powers of primes and then double of powers of primes. So 18, of course, would fit into that last category because it's 2 times 3 squared. Okay. And if I follow through on my idea of giving you table 1 from the book, table 1 will list a primitive prime for every prime number p, but not for this kind of a number. So there is no information in the back of the book for a number like 18. If this was 17, you could take the table and say, oh, there's a prime. The back of the book gives me a primitive root. And then you could just calculate powers of that primitive root. But for this problem, we don't have any advanced information about it, about what the primitive roots would be. So what we could do here is figure out, well, what is the order of a primitive root? So R is a primitive root of 18 if and only if the order in mod 18 of R is equal to phi of 18. And phi of 18, we could calculate that one. We just talked about the Euler phi function on the last example. So 18 would be, 2 times 3 squared. So phi of 2, which is 1. Phi of 3 squared is 3 squared minus 3, which is 6. Yeah, it would just be 6. So this should just be 6. This should just be 6. So we're looking for an element of order 6. And remember that the only elements that even have an order are the ones that are relatively prime to 18. So you're not going to be looking at 2 or 3 or anything like that, or a 4 or a 6. None of those numbers even have orders at all. In fact, there's only 6 possible candidates for numbers that would be primitive roots here, right? So they would just be the 6 numbers that are relatively prime to 18. Right, so the candidates, let's just make another note here. The candidates for the primitive roots it has to be a number that has an order, which means it has to be a number that is relatively prime to 18. So what numbers are relatively prime to 18? Obviously 1. What else? 5 would be a good one. 7 is a good one. 11. 13. And lastly, 17. Yeah, so those are the 6 numbers that are relatively prime to 18. And so these are the numbers that even will have an order. Nothing else does. Okay? But we need to have an element whose order is actually 6. I know without even taking a breath that 1 has order 1. How many powers of 1 do I have to take until I get back to 1 in mod 18? The answer is 1. 1 to the first. So that's not a primitive root. 17 is also never going to be a primitive root because it's really negative 1. Right? And negative 1, when you square it, is already back to 1. So the order of 17 is too small as well. Pretty much throw that one away immediately. So by the way, how many of these will actually be primitive roots?
It should be phi of p.
Exactly. It should be phi of 18, right? So if I look at phi of 18, that's phi of 6. And if you think about what phi of 6 is, it's phi of 2 times phi of 3. That's 1 times 2. It's 2. So out of the 6 candidates, we already know that there will be 2 winners. And we've crossed off 2 of the losers already. So it's just a matter of looking at the ones that are left in the middle here. And this is going to require a little bit of a brute force calculation. Let's just try 5. Okay, so we can try 5. Now, what am I going to be doing with 5 right now? I would like to calculate its powers in order to see in mod 18, what is its order. So obviously the first power of 5 is 5, and that's not 1 in mod 18. So the order of 5 is not 1. Could it be 2? Well, let's do it. Let's check it. 5 squared, that would be 25. Is that congruent to 1 in mod 18? I don't think so. So this is not congruent to 1 in mod 18. So the order of 5 is not 2. Let's try the next one. 5 cubed. Well, that's 125. This is where a calculator might be mildly useful here, just to kind of simplify these numbers. Now I want to know, is 125 congruent to 1 in mod 18?
It's congruent to negative 1.
Yeah, I think it's congruent to negative 1, guys, because if you take 18 times 18 times 7, sorry. If you take 18 times 7, you get 126. 126 is congruent to 1 in mod 18. Sorry, 126 is congruent to 0 in mod 18, which means these two things are congruent in mod 18. So the point is it's not 1 yet. Right?
But we know that if 5 to the power of 3 is congruent to -1, we can square it, which is 5 to the power of 6, which is congruent to 1 mod 18.
Okay, so 5 to the power of 6 is congruent to 1 in mod 18. Do we have to check, by the way, do we have to check the 4th power and the 5th power? We actually don't. Now, when I write this down, okay, let me be really clear here, guys. When I write this down, I already knew that this was true before I even started any of this other work. Because after all, this exponent is just phi of 18. Let's remember the Euler theorem. A to the phi of n is congruent to 1 mod n. If I use n equal to 18, this is the very first theorem in the chapter 7, right? If I use the n equals 18 and I plug in phi of 18 equaling to 6, I actually know that any number to the 6th power will be congruent to 1 already. So be careful when you write this down, it's sort of looking like you derived this through some big calculation. You did not. You already knew that this was true. Your only question was, could a smaller power of 5 have been congruent to 1? And the answer is no, because whatever smaller power that would have been would have had to be a divisor of 6. Remember this? For which powers of A, I think we phrased it this way. When is A to the H congruent to 1 in mod n? It was if and only if H is a multiple of phi of n. So I already know that, I'm sorry, this is not what I meant to say. Sorry, the H is not a multiple of phi of n. H is a multiple of the order of A. That's what I meant to write there. H has to be a multiple of the order of A. So, guys, I already know that this left side is true for H equals 6. The left side is true. The 6th power of anything is 1 in mod n. By anything, I mean anything relatively prime to n. So as long as A is relatively prime to n, I know that when I raise it to the 6th power, it will be congruent to 1 modulo 18. So the order of every number in mod 18 is a divisor of 6. So that would be a 1, a 2, a 3, or a 6. If you've ruled all of those lower powers out, if you said no, none of those could be the order of your number, then this becomes the order. Right. So what this calculation shows, guys, is that the order in mod 18 of 5 is equal to 6. Be careful, because I don't want to see on the exam, this is where people get into trouble. I don't want to see somebody writing, oh, 5 to the 6 is congruent to 1 mod 18, therefore the order is 6. That's not the reason that the order is 6. That was true before we even took a breath, right? The reason that the order of 5 was equal to 6 was because we ruled out these lower powers of 5, and I need to see that on your paper. Otherwise, it looks like the definition of order is a little bit fuzzy. Right now, I don't want that to be a fuzzy thing for this exam. So the order is the smallest power of the number that is congruent to 1 in mod n. So you have to rule out these other numbers first, so that then this becomes actually the thing that it was true all along, but now that becomes what the order of that element is. It's just the 6th power, and that is the right order for a primitive root. So 5 is a primitive root. Okay, so let's write that down somewhere. So So 5 is a primitive root of 18. I've got one winner right here, and that would be 5. The question is asking me to find all of them, but so far at least I found one of them. We know that there's actually 2 of them. So so far I've got 1 winner, I've got 2 losers, and I've got 3 more that are still in the running. That's kind of where we're at. So how do we find the other primitive roots? The other primitive root?
We want to take powers of 5, but by the numbers of the power, you need to see if it's relatively prime to 6. So that would
That's right.
one.
That's right, Kim. Yes. So we are going to, one thing we hopefully remember, I think it was theorem 8.4, is that all of the primitive roots are just powers of any one primitive root that you write down. And which powers? Those powers that are relatively prime to phi of n. That's why there's phi of n primitive roots. Because you're taking exponents that are relatively prime, not just to n, but to phi of n. So relatively prime to phi of 18, which is 6, what numbers would be relatively prime to 6? Well, that would be 1 and 5, right? Those are the 2 numbers that are relatively prime to 6. And so my primitive roots of 18, would be 5 to the 1st power and 5 to the 5th power. And if you reduce 5 to the 5th in mod 18, you're basically going to just calculate this out fairly quickly. Let me just see if I can do this kind of quickly here. 125, didn't we already say that was -1? So this is -25, because it's -1 times 5 times 5. And if I'm in mod 18, -25 in mod 18 becomes 11. This is in mod 18. So 11 is my other winner. 11 is also a primitive root. So I've got 2 of them, and they are 5 and 11. Now, by the way, to get this second primitive root, you don't have to do it this way. You could just go back and say, oh, let's just start with 11. Let's calculate the 1st, 2nd, and 3rd power of 11. And you could just confirm that none of those are congruent to 1 mod 18. So you could take just the way we did with 5 here, you could just start over with any of those other candidates. You could do it with 7 or with 11 or with 13 and just raise them to the 1st, 2nd, and 3rd power. And as long as you don't get back congruent to 1 in mod 18 with any of those powers, you'd have a primitive root. You already know that you're only going to succeed twice. Before you even start looking at your list, you know there's 2 winners there. So that's a very helpful thing. Yeah. And so you don't have to use the fact that once you have one primitive root, all of the others are just powers of that primitive root. But it's good to know that, and it's good to review that. So yeah, so does that look okay? Once you have a primitive root, remember that we can make our little table of indices. Let's take r equals 5 and just make sure everybody understands how this table works. You can make a 2-row table, and you can make your own table of indices. I might make you do this. Like I might make you make a table of indices on the exam. And so, you would have 2 rows here. One row would have the x values on it, and then the other row would have the index of x values on it. We did this in class for 17, the thing with 17 was a prime. And so every number from 1 through 16 was represented in that table. For this table, even though we're using a larger number, which is 18, the table is much smaller because your only x's that you're even going to have an index for at all are the 6 values of x that are relatively prime to 18. You can think about it this way, guys. How many different index values can you have? Well, you can only have sort of 1 for every power of 5. You have 5 to the first, 5 to the second, 5 to the third, 5 to the fourth, 5 to the fifth, and 5 to the sixth. And after that, you're done. There's nothing else you can have. So you're only going to have 6 different powers of 5 that ever show up. So you shouldn't have more than 6 things in your table. If I ask you to make this table, I want to see only the numbers relatively prime to 18, or in general n, listed on that top row. And now how do you fill out the bottom row here? You know, this first one is really, you know, it's 5 to this power equals this number, right? So it's like, what power of 5 gives me a 1? So you could say 6. You could also just say 0. That wouldn't be wrong. But I think in the definition, we defined the index to be positive values. So it was supposed to be the first positive integer for which that exponent gives you the number on top. Okay, so let me make sure this is coming through on my notes here on my video. So what power of 5 gives you a 5? The first power, right? The way I actually usually fill out this table is not from left to right. What I would do is I would say, okay, well, if there's a 1 there, then where does the 2 go? I don't figure out 7 yet. I figure out, okay, well, where would the 2 be? Wherever the 2 is, what we're saying is that 5 squared is the number above it. Okay, 5 squared, that's 7 in the world of mod 18. So that actually is that value. 5 squared would be 7. And then, okay, where does the 3 go? 5 cubed. Now, when you're thinking about 5 cubed, you're probably thinking 125. I would prefer for you to think of 5 cubed as 5 squared times 5. So 7 times 5 is 35. And in the world of mod 18, 35 is the same as 17. It goes over here. Actually, this last number is always going to be half of the way to the order of the element. So the order of the element is phi of n, phi of 18. So 3 happens to be phi of 18 over 2. Yeah. Because why is that? Why is that? Well, because remember, guys, just to be recalling a homework problem you did. Remember that so I'm going to switch to mod p for just a second. I know 18 is not a prime, but let me just remind you the way we wrote this before, because it works the same way here. This is just Fermat's little theorem. Anything to the p minus 1 power is congruent to 1 in mod p. This factors as r to the p minus 1 over 2 minus 1 times r to the p minus 1 over 2 plus 1. We have seen this a couple of times. It's a very useful observation. But we know that if r is a primitive root, we can't get back to 1 this few powers. It has to be order p minus 1. So this is not congruent to 1. So then this is the one that's congruent to 1. And guys, in this table, 17 is really just like negative 1. So what power of my primitive root am I talking about here? Half of what the total order of that element is. I can take this whole equation and everywhere you see a p, sorry, everywhere you see a P minus one, I can rewrite it as phi of n. Right? So this is just phi of n over two, this is just phi of n over two. So the phi of n, the phi of 18 is 6. You divide that by 2, you get 3. That's the number that goes here. All right, where does the 4 go? Let's see. The way I would figure it out is that the 3 is sitting under negative 17. Now, under 17, which is negative 1. Multiply by 5 again. That's negative 5. And in mod 18, negative 5 is the same as 13. So think about it that way. And of course, that means this is going to be the 5 right here as well. 5 to the 5th is definitely 11. Which is actually, we already knew that because we calculated this calculation here earlier. We already kind of knew that that was where that was going to go. Okay. But this second row can be a jumbled up mess. It makes more time-saving sense that you don't fill it out from left to right. Fill it out sort of 1, 2, 3, 4, 5 on the bottom row in order like that. Each time you want to go to filling out the next number on the bottom row, you're just multiplying by 5 on the top row, or in general by r, whatever that primitive root is. Yeah. So that becomes a very condensed table in that case. Okay. Feeling pretty good about a lot of this stuff. Yeah, I guess I've got a couple more problems, but a lot of this is a little bit redundant of what we've already kind of gone over. If I stop a little early, what I'll end up doing is I'll start with these on the next review and on Wednesday, the ones that I didn't get to, but I think I've done pretty well with covering most of this. But let's just try number 5 here. So let R be a primitive root of P. Let's try to prove that the index relative to R of P minus A is congruent to the index relative to R of A plus half of P minus 1. And this would be in mod P minus 1. Yeah. In mod P minus 1. Okay. Any thoughts about where to start on something like that?
Can we start with using the rules of indices to try to split up the index of P minus A?
Is there a property that allows us to split up the P minus A in the index?
I don't think minus, but there is a property for plus.
We have to be really careful here because this is something that the gets people in trouble with their algebra. Is there a property for the natural log of x plus y?
No.
There is not. What you have is you have a property for the natural log of x times y, and that breaks up in terms of addition. So just remember, if you're a little confused about what are the properties that you have, go back to logarithms, and if you know your properties of logarithms, then you also know the properties of indices because they work exactly the same way. So I actually claim that we really can't do much with the left side at all at this stage. Yeah.
You multiply everything by 2.
Well, I certainly could do that. Yeah.
And then P minus 1.
And then the P minus 1 would go to 0. So that would be a thought. Now keep in mind, we're working backwards if we do that. Okay, so because this is what we're trying to prove. So if you take this and start manipulating it, you just need to make sure that all of those manipulations are reversible, because this is actually supposed to be the conclusion of your proof, not where your proof starts. So at that point, you almost need to be off on scratch paper first, kind of playing around with this. And you know, it's not a bad thought. So we could kind of like your thought here, the scratch idea. This would be maybe on my scratch paper would be to just double everything. So 2 times the index relative to R of P minus A is congruent to 2 times the index relative to R of A plus P minus 1. And this is still in the same mod, so we don't have to double the mod for that to be true.
Or we can just start from the beginning with our assumption that R is a primitive root of P. Therefore, the ordered of P of R is equal to P minus 1.
Yep, that's possible too, Kim. Let me just pursue this for just a quick second. If I have this statement right here, and I wanted to go back to this statement, I would now have to divide by 2. I always get nervous when I divide congruences through. As long as I'm dividing by something that's relatively prime to my mod, I would be okay with that. Let's see, what is my modulus going to be? If P was 3, we might have a problem, right? Because then if P was 3, this is a mod of 2. And we might have just, I mean, going this direction would be fine. But again, we've got to ultimately go backwards. So now you could maybe make a case that, all right, well, P equals 3 is a special case. Let's not worry about it. And then you could like keep going with this. And you can say, all right, that part goes away. And now we could like put squares in, put these up as squares and like try to cancel the indices or something. But you'd ultimately have to try to get back to something that was a clearly true statement. So you could say, yeah, I'll go ahead and put the P minus A inside. And then I would do the same thing here. Put the A squared inside, and this would still be in mod P minus 1. And actually, if you did that, so do we have any knowledge about when the index of a number is congruent to the index of another number? Does that tell you anything about the numbers themselves? So P minus A squared as compared with just A squared, right? You're basically exponentiating both sides. And that's okay in the original mod. So this would not be in mod P minus 1. This would be back upstairs in mod P. Actually, if you look at this statement, it's true. This is true. In mod P, the left side and the right side here are absolutely the same thing. Because in mod P, the P becomes a 0, you have negative A. Well, squaring negative A is no different than just squaring A. So this actually is true. And if I then was to run my scratch work backwards and say, well, oh, if these two things are congruent, then their indices will be congruent mod phi of P. And therefore this is true. And therefore this is true by properties of index. And then I guess as long as P does not equal 3, I can cancel the 2's and get the statement that is up there. So at least for every value other than 3, I think this proof does work, Weston. But you are working backwards and you're having to make sure that everything is reversible. Yeah. And for P equals 3, if R is a primitive root of 3, actually, that's going to tell you that R is actually 2. That's the only primitive root that 3 is going to have. The number of roots, guys, it's phi of 3. Phi of 3 is actually equal to 1. Because if you take phi of 3, that's phi of 2, and phi of 2 is 1. There is only one primitive root of 3. So if p was 3, and I said let r be a primitive root of 3, I'm basically saying that r has to be the one and only primitive root that there is, which would be the number 2, which actually is the same as -1 as well. So, I mean, it would be very easy to prove this for p equals 3 directly. We could do that. So let's not bother with that. I want to go back to what Kim said a minute ago, which is a totally different track. Instead of working backwards from what we're trying to prove, another way to approach this would be to just, use the fact that r is a primitive root of p and work from there. One thing we know is that if r is a primitive root of p, I've sort of almost not erased it, is that if r is a primitive root of p, so here's another way to solve the problem, is you can then look at r to the p minus 1 over 2. So this is a way that doesn't involve backwards scratch work, but just goes directly forward. And what is this congruent to in mod p?
It should be congruent to -1.
That's right. It should be congruent to -1 in mod p. Because it has to be, well, it goes back to the thing that's sort of half erased on the board over here, where I was factoring r to the p minus 1 minus 1 into 2 factors. So yeah, this is what it would have to be. And now you can just take this and hit it with index on both sides, right? So if you now just take the index relative to r of r to the p minus 1 over 2, that should be congruent to the index relative to r of -1, and this would now be in mod of p minus 1. Yeah, so we would know this much, and of course this thing on the left side, the index relative to r of some power of r, that is just the exponent itself. So just the way logarithm of e to the x is just x, these are kind of inverse functions that gives you exactly what you see there. Okay, so I know what the index of -1 is. So the question is, let's just see if we can work this out. So if I then want to calculate the index relative to r of a, which is something that's part of the question here. And I add the p minus 1 over 2 to it. So I'm kind of starting with the right-hand side. If I just start with the right-hand side of what I'm trying to prove here, that's what I got here. I can take that and I can replace that second term. I can replace that second term with the index relative to r of r to the power of p minus 1 over 2. And now I can use my properties of index to combine that into a single index here. Actually, before I do that, what I could really do first is change this index relative to r of r to the p minus 1 over 2. I can change that to the index of -1. By the way, all of this is going to be in mod p minus 1. Okay, so just to be clear, I'm trying to prove in mod p minus 1, I'm taking the right-hand side, and I try to convince you it's the same as the left side. I can take p minus 1 over 2 and replace it with index of -1. That's kind of what we saw here. The p minus 1 over 2, or p of n minus 1 over 2, was the index of -1. 17 is the same as -1 in mod 18. So I can certainly do that. And now I think you see how to finish this. This becomes very straightforward. This is just the index relative to R of the product of A with -1, which is just negative A. And I know where I'm trying to go. I'm trying to get P minus A. Well, you can add or subtract a P all day long without changing the essence of the number that you're taking the index of. So you can just go ahead and change negative A to P minus A, and you end up getting this. So the trick here is to recognize that the P minus 1 over 2 is the index of -1. So in the proof, we take P minus 1 over 2 and we replace it with the index of -1. From there, it's just a couple quick steps. It's not too long. Okay. Nice. Guys, I think this exam will have, this is like a baby theoretical problem. It's actually, I spent a lot of time looking at different ways of thinking about it, but when you boil it down, it's not very long. It's a pretty short solution. So you'll have a mix of things like this that will be short. I'm not going to ask you a theoretical problem that's going to take you a whole page to figure out, other than the proofs you're learning already. So the theoretical ones are going to be short and sweet. Short and sweet. Where will you spend more of your time? Well, maybe there'll be a complicated Legendre symbol to calculate. Or maybe there'll be a proof involving like the phi of n, using the formula for phi of n to do something. Or maybe working out a table of indices, something like that. Those are the kind of things that maybe take a little bit more patience with the computational aspects of it. But as I look at my sheet here, there's a couple things I didn't do. Maybe I'll do one more problem. Do I have time for one more? Or should I call it a day? You guys are here. Why not, huh? Okay, let me do one more. This won't take long. I just realized I haven't maybe quite done something quite like this. I'll do one last problem. I know it's after 5 and I need to take a break because I haven't been feeling the best myself this weekend. So I'd like to wrap this up sooner than later. But let me just do one more problem and then I'm going to go take a break before I have any office hours. I need a full 2 hours to recover myself. Okay, so let's try to prove this last thing, that if P is prime, then I would like to try to prove that phi of P to the K. So this would be the number of primitive roots of P to the K. Remember that P to the K will have primitive roots, and so this is how many it will have. There is actually a nice formula for it. It is P to the power of K minus 2 times phi of P, sorry, not P. Let me just write it this way. Phi of the quantity of P squared minus P. This, I guess you could call this a theoretical problem, but actually it's mostly a computational one. It's mostly computational and it's not anything too long. I just want to kind of finish on a nice, easy note here. So let's just see if we can do this. You basically are just going to use the properties of the Euler phi function for this. So on the left side, if we just start phi of P to the K, working on the inside, what is the formula for phi of P to the K? P to the K minus P to the K minus 1. So we can put that on the inside. And how would you recommend that I evaluate that P value?
Factor.
Yeah, let's factor it. Let's factor it as good as we can. How about we take out as many powers of P as we can, which would be P minus 1 of them. It would leave me with P minus 1 as a factor of the inside, yeah? And what can I do with that? I can separate. I have to make sure, are the two things I'm separating relatively prime? Well, p minus 1 has no common factors with p because they're two adjacent numbers. They never would have common factors. So it is perfectly legitimate to split that apart. So this is just phi of p to the k minus 1 times the quantity of phi of p minus 1. All right. Keep in mind where you're trying to go. Any thoughts on what I might do from here?
Well, phi of p to the k minus 1 is the same as p to the k minus 1 minus p to the k minus 2.
Hey, there we go. Exactly. This is just phi of p to the k minus, sorry, it's just p to the k minus 1 minus p to the k minus 2 times phi of p minus 1. And what do you suppose I'm going to do with that? Factor again, right? On the front part, I can pull, and I see how many powers of p I want to pull out. I can pull out k minus 2 powers of p, leaving me with p minus 1 times phi of p minus 1, yeah? And where am I going to go from there? I ran out of room, but I can come back over here and finish it. What do you suppose I want to do? You can kind of look, it's really helpful to look at where you're trying to get to. The power of p in the front is already taken care of. How do I make the rest of it work?
You can multiply the p minus 1 back into the phi of p minus 1.
I would do it differently.
We calculate phi of p squared minus p.
We could go to the conclusion. I'm not going to do that. We could go to the conclusion and like work it out and make it reconcile with what we have here. But I would, just because I'm going to try and get there, what's the fastest way you could get me to the conclusion here?
P minus 1 p. So
P
Yeah,
minus
p minus 1 is just phi of p. I know we don't usually use the formula that way around, but that is the best way to do this. P minus 1 is just phi of p, and we're multiplying that by what's already there, which is phi of p minus 1. And now we combine this together again, and I get the product here. These are relatively prime, so you do get p squared minus p. Edgar, what you said earlier about calculating phi of p squared minus p, that would have been fine. If you had sort of worked from the bottom and kind of worked backwards through the steps, you could have matched it up with where you were at in the calculation, and it would have worked out great. So this is really a straight calculation. Just notice how nice and organized the writing is. I have equal signs between my steps. I have nothing but white space on the left side. This is a well-written proof. If people start manipulating both sides of the equal sign at the same time, it becomes discombobulated and it's hard to follow what the train of thought is. So I like this single file, step-by-step list of deductions from one to the next. But in terms of the actual number theory, it's not really that deep. It's just using the properties of the phi function to go from there. So, all right, well, I'm a little worn out. As I was telling people earlier, I've been a little bit, not sick, but I've been having some issues, just musculoskeletal stuff, and woke up with a feeling like I got sucker punched in the eye. I have no idea what I did to deserve that, but I woke up not feeling great on that score. So I'm going to take a break and we'll call this good. I got through 6 problems, I think. There were only 2 that I didn't do, and neither one of those other 2 is really anything critical for right now. So I'm just going to leave it at that and let you guys get on with your studying and ask me some questions if there are any during my office hours. I'll be back at 8 o'clock. If you're going to work on the homework and you have anything you want to check off with me on that, feel free to stop by. I'll be glad to help out. Thanks for coming too. Appreciate it.
Thank you,
Thanks,
Dr.
guys.
Bye.
Thanks. Bye-bye.